When you're finding areas by integration, it makes sense to follow these steps. Always start with a sketch and make sure that your sketch shows any important intercepts or intersections. Second thing to do is to basically split up your function into the sections that are above or below the axis involved. So that way you're going to have a few separate definite integrals. So in this example down here, which has a function that I'm not even sure the name of, let's just call it y equals f of x. I can see that I've got x-intercepts at A, B and C. So if I'm going to find the area that's between the curve and the x-axis, I can see straight away that I need to break my area up into two sections, and I need to calculate those two sections separately. So, second step, write and evaluate the definite integrals that you'll need to find. Now, number 3 is consider the signed area of each section, and then add them up. So, of course, when I find the definite integral here from A up to B, that will be the exact same number as the number of units squared of the area. So all I need to do is take that number that the definite integral gives me, and that is the area. Whereas for this section here, I know that the area will be the negative version of whatever answer I get as the definite integral, because the definite integral here will be negative, and yet I know that areas must be positive, so I need to change that by putting a negative in front of it. So for example, if the definite integral here gave me an answer of negative 1.5, then I would reason that this area here must be not negative 1.5, but just 1.5 units squared. And then I need to add up the two areas that I've found, in this case if there's 2, and the last thing to do, of course, is to add square units to your answer. And you can write units squared like that, or you can even write u squared for units squared. In this example, we need to find the area enclosed by the x-axis and this curve. Now, it's been given to us in factorised form, and that's going to help a lot when we're finding x-intercepts. But we also know that when we're finding area, we need to integrate. And we can't integrate something like this very easily. We're going to have to expand it out and integrate it one term at a time. So before I start, I might just go ahead and do that expansion. So underneath here, I'll expand this part in one go and then put the x's in after. You can do all 3 things in one go if you want to, but I don't want to make a mistake. So I've got plus x minus 2x minus 2. And when I expand all that out again, I get x cubed minus x squared minus 2x. Now I have a form that's going to be easy to find the primitive of, and I have a form that's going to be easy for finding intercepts. So a quick sketch here. First, look at what type of curve we have. It's a cubic curve, and it's a positive one. So I know it's going to have that basic shape going from low to high with some sort of wobble in the middle. So the next thing to do to put it on here is to actually find the x-intercepts. And those occur, of course, when y equals 0. Now, if we've got 3 parts multiplied together, they will only equal 0 if one of the 3 parts was 0. So either x was 0, or x was negative 1, because negative 1 plus 1 would be 0, or when x is 2, this part would be 0. And that gives me my intercepts nice and quickly and easily, just by imagining that I'm going to let y equal 0. Now, if you want to, you can write down let y equal 0, and then you can actually write down 0 equals and recreate all of that. But you're probably getting to the stage where you can do this thinking in your head. And as long as you've got your intercepts in the right place, by drawing them in, an examiner will be able to see that you've done this thinking. So feel free to write it down if you still need to, but with one as simple as this, we can often just imagine letting y equal 0 and think about what these parts would need to be. So now we can go ahead and draw in that rough shape of a cubic curve, and that's all the detail that we're going to need. Now we're finding the area enclosed by the curve and the x-axis, so there's 2 parts to it. There'll be this part above the x-axis and this part that's below. So we need to think ahead and think the definite integral of this part will be equal to the area of that part. The definite integral here will come out as a negative, but we need to then convert that into a positive number, add the 2 parts together, and that will give us our total area. So there's a few ways to do this. You could write area equals and come up with a long set of integrals and add them together. and subtract the negative one, which will be the same as adding it. That will account for its negativeness. Or if you prefer, you could say, let's call this area 1 and area 2. You can calculate them separately and then add them up at the end. It's up to you. I'll make them separate this time, but in our next example, perhaps we'll smush them together. So let's call this area A and area B, for argument's sake. You can name it whatever you like. So for area A, we need to find the integral, and we know it will be positive, so it will be equal to the area, from -1 up to 0. Now, we're going to want to find the primitive of our function, but I don't want to put this in. I want to put this version, because this one I can integrate one term at a time nice and easily. So I'm finding the definite integral of this. Now you can put all of that in brackets to show that we are integrating the whole thing, and that will give us the area. So let's go ahead and calculate it. First step, big square brackets. Let's integrate one term at a time. We need to add 1 to the power, divide by the new power, double check that that differentiates back to this. Yes, it does. Add 1 to the power, we've got minus x cubed on 3. And here, add 1 to the power will give us 2. Dividing by the new power of 2, though, will cancel here. So this part, x squared. And again, just double check. Does minus x squared differentiate to -2x? When you bring the 2 down the front, change that to 1. Yeah, it does. So always double check your integrating. Now put your bounds in. And on the next step, we're going to sub in the 0 and then subtract the subbing in of the -1. Now, looking ahead here, if I sub 0 into all 3 of these terms, all of them are going to be 0. So I'm going to have 0 minus 0 minus 0. You can write that down if you want to, just to be really complete, but I can see that I'm going to get nothing there. So I'm going to actually just leave that part out. But don't forget that if this whole part's 0, and I might just put it in as a placeholder, I need to then subtract, with brackets, the subbing in of this. And this is where you could make a mistake. So writing the 0 is not so silly, because it reminds you I've got to sub in this and then take away the subbing in of that. A lot of people forget this sign. Okay, so now let's sub in -1 for x. Now if we have -1 to the power of 4, that just gives us 1. So we'll have 1/4 there. -1 to the power of 3 is -1, but we're subtracting -1. That's like adding. So we'll need to add a third. And then here, -1 squared is 1, but we're subtracting it. So we are subtracting 1, and those are my 3 parts. Okay, now figuring out what we've got. Well, we have 3/12 plus 4/12, that's 7/12, minus 12/12, that gives me minus 5/12, but we're subtracting minus 5/12. So I know I just have 5/12 here. Now, you might choose to do that whole step on your calculator. Feel free, make sure you don't mess it up. I haven't got mine on me, so I'm using my head. Now, this area is positive, and just check that makes sense. Yes, because it's above the x-axis. So this is now an area, and I can say that that's in units squared. Okay, now for area B, let's squeeze that in over here. I know that it's below the x-axis. So when I find my definite integral between here and here, the answer is going to come out as a negative, but my area needs to be positive. So I can make up for that by just putting a great big negative sign out the front of my integral from 0 to 2 of all of this same function as I had before, so the working looks very similar. Now I've already integrated this one term at a time, so I can use the exact same set of brackets for my second line of working, and that saves me a bit of time just copying it across. And my new bounds 2 and 0. Now don't forget that on the second line of working you'll need to put that negative sign out the front, because if it's out the front of the whole integral, it'll need to be out the front of the square brackets as well. Alright, subbing in now. I'm going to keep brackets because I've got that negative sign. Subbing in 2, I've got 2 to the power of 4, that's 16, divided by 4 is 4, minus 2 cubed, that's 8 over 3, minus, hold on, that's meant to be an x squared, minus 4. And then I need to subtract something. Now you might be thinking, let's put big square brackets here, because if this was a number other than 0, I'd be subbing it in and I'd be having 3 more terms out here, wouldn't I? And there's a lot of potential to make a classic sign error here. Now I can see though that when I sub 0 in, all 3 of these terms will be 0. So all I'm taking away is actually 0, which you can write like that if you want to, or you can leave it out, saying it's not going to make any difference taking 0 away. And in this case, I don't really need the big square brackets. But if I had a number other than 0 there, I'd use them just to make sure I don't make a mistake with this. All right, 4 minus 4 is nothing. So we just have negative 8/3. That's positive 8/3, which I'm going to write as 2 2/3 units squared. So now I can see that my error is 2 2/3 units squared plus another 5/12 units squared. Would be nice to put them both in twelfths, wouldn't it? So this is 8/12, and if I add 5/12, I'm going to have 3 1/12. So total area equals 3 1/12 units squared, and I'm finished. Now in these sort of questions, don't forget to look out for symmetry, because if you can spot that you have an odd function, you might have a situation where these parts might have been the exact same size, for example. And if you found the size of one of them, then you'd know the other one and you could just double it. That would save you time. You might also spot that a function is even, which of course means that it has symmetry around the y-axis. Well, that doesn't look so good, does it? Symmetry around the y-axis, which means that, again, if you're finding an area on either side that is the same size, you can just find one of them and then double it.